Hi guys, we're going to do a lab today that deals with forces and acceleration. So it deals with Newton's second law, but it also brings together gravity and friction and a few other things. So you need to have your Newton's laws lab handout open, and let's get started. The pre-lab I want us to do together. So let's talk about number 1. Essentially, when objects are being accelerated by gravity, they accelerate at 9.8 meters per second squared. So gravity is pulling on this weight down here with a force that would accelerate it at 9.8 meters per second And the string is connected to our car, which is on a horizontal ramp. The force that gravity pulls on our weight with has to accelerate both the weight, also the string, and the car. So the actual acceleration of the system, all of these objects together, the weight, the string, and the car, is going to be somewhat less than 9.8 meters per second. So let's work through figuring out a prediction for the actual acceleration of the system. Now, number 1 is asking if the car had negligible mass. In other words, let's assume that it has no mass. What would the acceleration of the car and weight be? So if this gravitational force were accelerating mass and this mass is 0, then this whole acceleration should be the same as the gravitational acceleration. So 9.81 meters per second per second. On to number 2. You need to draw a free body diagram of the car and show the 4 forces on it as it accelerates down the ramp. So to do that, bring your cursor down here and then choose Insert, Drawing, and you want a new drawing. So you'll create a new drawing, and that will be your free body diagram of the car. Does not need to be anything fancy. So, it's still loading. It's kind of slow because I've got a lot of things going on. So I'm going to add a shape. Does not have to be a fancy shape, just a box or a circle. That's it. There's our car. No need to add wheels or anything, just a box. Then you can add your arrows like that, and give the 4 forces that are acting on it. I'm just going to do some quickies, right? I drew my line. It's supposed to, there, it has an arrow on the end of it. And then use a text box to label that. That one happens to be the most typical one, force of gravity. And that's good. I'll let you figure out the other 4. So remember, you've got gravitational force. You have to have something opposing it because this car is not accelerating up or down. It is accelerating in the horizontal directions, though, so figure out what those size forces should be and draw your free body diagram. When you're done drawing your free body diagram, hit Save and Close, and it will deposit your drawing right in the space below number 2. There. Okay, and then we will keep going on. Number 3, what is the force that the weight, which has a mass of 100 grams, pulls down with? So we're going to use that equation from Newton's second law. So F equals ma. This is really slow. We want to know what the force is. The mass is the mass of the weight. So I'm going to call that mass of the weight. And I don't want you to change that. everybody in class used 100 grams, and that's what I'll be using today, is a 100 gram mass. Now, when we use Newton's second law, we need to have our mass in kilograms. So you will need to convert this into kilograms. I will let you remember how to do that. You might have to think back to last fall, or you might have to look through your notes or Google it, but you need to convert all masses that we take today from grams into kilograms. And we know also the acceleration that the force is being caused by is the acceleration due to gravity. And on Earth, the acceleration due to gravity is always 9.81 meters per second on Earth. Not always true in other parts of the universe, but on Earth it's at 9.81. So the force, we just have to multiply those together. The force acting on this is the mass in kilograms times the acceleration due to gravity, 9.81 meters per second, and you'll get your force. And that is the force that is acting on our mass, and it's also the force that's acting on the entire system. So whatever you get here, you're going to use later on in the lab. All right, then you have to use the triple beam balance, and I will show you what I mean by that. So if you look in your screen, you see the triple beam balance over here. I used that earlier, and I got a mass for you to use. That mass is 0.4265 kilograms. That is the mass of the CPO car with the string and the 100 gram mass on it. So I measured all those three things together and got 0.465 kilograms. All right, so now we have to figure out what the theoretical acceleration of the car and ramp is. So we have the force that you measured in number 3. So you'll use the answer to number 3 for your force. The mass that you'll use is the answer to number 4 right above, and then you'll use that to find the theoretical acceleration. So this is like, if nothing else is impacting our car as it accelerates across the ramp, then this is the acceleration we should get. All right, I'll let you guys figure that out. I'll give you a hint though. Your answer should be between 2 to 3 meters per second. So if you get an answer outside of that range, then double check your math and see if you made a mistake. All right, now I have recreated this data table on a whiteboard, and I'm going to enter data on it. Just to remind you, the width of the wing of the car, remember that wing on the car, I'll show it to you in a minute, is 5 centimeters, and we need to convert that into meters. So I will let you figure out how to convert centimeters to meters. Again, think back to last fall, and we've done this before. You'll need to use it, the width of the wing of the car, in meters while you do this lab. Okay, I'm going to switch to a different view. So here you see the car and ramp all set up. I have the CPO timer box right here. I have photo gate A, photo gate B, and the car, too many wires. The car is going to go through those photo gates. And we will make some measurements. I'm going to pause here and make a second video because this is going to get long. All right, bye.